comes to its end, has been more or less completely consumed, the star will shrink. It must shrink because the red arrows become smaller than they were, and gravity takes over. And gravity takes over and squeezes the star under the influence of the gravitational force. Then again, gravitational potential energy is again converted to kinetic energy, because the fact that it shrinks means that gravitational potential energy is converted to speed, and speed means temperature. So the core now becomes hot, and it becomes so hot that now the helium can start its fusion cycle, and it can make carbon. And so essential is, as we see later, that once a particular element, like hydrogen, has been consumed, that the core must shrink because of gravity. And when the core shrinks, the temperature goes up. That allows then, in this case, the helium to ignite, because helium fusion takes place at a higher temperature. Then there comes a time that the helium has been mostly consumed, and then the carbon that was formed by the helium may take over. In other words, the core shrinks again, temperature goes up again, and the carbon will now start to burn and make oxygen. And with stars with a mass less than 8 solar mass, that in general is the end of the nuclear fusion. In other words, when the carbon has been used up and has formed largely oxygen, it is true that the core shrinks, but the temperature doesn't get high enough to ignite the oxygen. And so the nuclear fusion stops. And clearly, when the nuclear fusion stops, of course, gravity is the only force that we have. Each nuclear cycle produces more energy per second than the previous one. So the helium cycle produces a higher luminosity than the hydrogen cycle. So that means when the helium ignites, the pushing of the nuclear fuel becomes larger than it was under the hydrogen, and therefore the star will expand. The red one wins over gravity. And it expands so much that when that happens to our sun, will happen in about 5 billion years, the sun will become 100 times larger than it is now. We call that a red giant. Imagine that the sun is 100 times larger than it is now in the sky. Of course, it will be the end of Mercury, the end of Venus, and the end of the Earth. It's clear. But that's what happens when the luminosity of the core increases. Now, when the nuclear fusion will no longer start, gravity is the only thing that there is. And so the core becomes smaller, but not hot enough to ignite the oxygen. The star is now so enormously big because of the luminosity went up so much, that if it is 100 times larger than it was before, the atmosphere of the star is very loosely hanging in there. Because remember from your physics that the gravitational pull is inversely proportional to r squared. So if the atmosphere goes 100 times further out, the force on the atmosphere becomes extremely small, and over a period of maybe billions of a year, the star gets rid of its entire atmosphere, and what is only left over is the nuclear fusion, the core, which is in this case largely carbon and oxygen, and we give that a name. We call that a white dwarf. And I will now talk about how white dwarfs were discovered. Bessel was a mathematician who made very careful observations of the position of Sirius, which is the brightest star in the sky. He made very accurate positions of the motion of Sirius, and he concluded Sirius must have an invisible companion. He concluded that there were really two stars, even though we only see one, and that they go around each other in 50 years. We call that a binary star system, or double star. So he predicted it's a binary system. The period is 50 years, and he calculated roughly that the invisible star had a mass comparable to our sun. But the star was not seen. And so he wrote then an extremely famous letter to Alexander von Humboldt, which I translated for you. He said, Bessel said, I adhere to the conviction that the star Sirius is a binary system consisting of a visible and an invisible star. There is no reason to suppose that luminosity is an essential quality of cosmic bodies. Visibility of countless stars is no argument against the invisibility of countless others. Think about this, what he will say. We only believe what we see. He was creating astronomy of the invisible. He said, if we can't see it, that doesn't mean it's not there. And I repeat that last sentence. Visibilities of countless stars is no argument against the invisibility of countless others. Nowadays, if you look at all the fields of astronomy, 95% invisible. Ultraviolet astronomy, invisible. Infrared astronomy, invisible. X-ray astronomy, invisible. Gamma ray astronomy, invisible. Radio astronomy, invisible. So practically anything that we do nowadays is invisible, except that very small part of the visible light in the electromagnetic spectrum. This is a very, very small part of the total spectrum. He was the first to mention the possibility that what we don't see could still be there. What determines the luminosity of a star? I'll give you a small test. Suppose we have two stars which have exactly the same temperature, just for simplicity. But the radius of one star is twice as large as the radius of the other. Which of the two do you think has the highest luminosity, radiates most joules per second? Is it the larger one or the smaller one? The larger one. If the radius is twice as large, how much more energy do you think it radiates per second than the smaller one? Do I hear twice as much? 4 times as much. And why 4 times as much? Because the surface area of a sphere is proportional to the radius squared. In other words, the luminosity, and I just mark is how many joules per second, how many watts are generated. The luminosity must be proportional to 4 pi r squared. Then in addition there is a constant which is not so important right now. You can look up in your physics book what the value of that constant is. I will just write down here sigma, called the Stephan Hopkins constant, but forget about that one. I'll give you a second test. Suppose we have two stars which have exactly the same radius, but the temperature of one star is twice as high as the temperature of the other star. Which star do you think will radiate as the highest luminosity? The highest temperature. How many more times do you think will be the luminosity? What do I hear? 4? Do I hear 8? Do I hear 16? Yes. Very good. Good school. Yeah, it is proportional 10 to the power of 4. So look at that, because that's going to be very important. P to the power of 4. In Cambridge, which is the town where I live in the United States, there was a telescope builder, his name was Clark. And he had built in the 19th century a new 18-inch refractor, and his son Alvin, in 1861, tested his father's new telescope, and he pointed it at the sky, and what did he see? When he looked at Sirius, he saw the bright star that we all see, but he saw next to the bright star a very faint star, which was about 10,000 times fainter than Sirius. He immediately realized that that obviously was the star that Bessel had predicted, the invisible star. Bessel had said, well, the mass is about 1 solar mass. Now look at this equation. How can we make one star 10,000 times fainter than the other star? Well, people said that's very easy. It is reasonable to assume that perhaps the temperature is the same of Sirius A and B. So all you have to do is make the radius of Sirius B, which is the faint one, 100 times smaller than Sirius A, because 100 squared is 10 to the 4th. So if you make it 100 times smaller, no big deal, you can explain the factor 10 to the 4th. But if the star is 100 times smaller than, say, our sun, or Sirius, then the volume is 1,000,000 times smaller. And if the volume is 1,000,000 times smaller, then the density of that star is 1,000,000 times higher than normal stars, like our sun. Our sun has a mean density of about 1 gram per cubic centimeter. And so they would then have to conclude that Sirius would have a density of 1,000,000 grams per cubic centimeter, and clearly it was believed that that's total nonsense, that that's not possible. So that idea that Sirius B was 100 times smaller was immediately rejected. So what else can you do? What can you do with the temperature of Sirius B so that it emits 10,000 times less energy than Sirius A? You have to make the temperature low by how much? A factor of 10. So if you make Sirius B 10 times lower temperature than Sirius A, you can explain the factor of 10 to the 4th. What would that mean about the temperature of Sirius B? Our sun has a temperature of 6,000 degrees. It's not too different from Sirius A. So it would mean then that the object would have a temperature of about 600 degrees, typically 10 times lower than our sun. Why not? People had no problems with that. So they concluded that Sirius B was so faint because it was a very cool star. In 1915, WalterLewin measured the temperature of Sirius B. That was possible because spectroscopy was being used in those days. You look at the spectrum of the star, started around that time, the astronomers did that, and if the star is very cool, then there is a lot of red light in the spectrum, and if the star is very hot, there is a lot of blue light. And by looking at the spectrum, just as you know that the sun produces a spectrum when you see a rainbow, by looking at how much red there is and how much blue there is, astronomers can quite accurately estimate the temperature of a star, just by looking at the spectrum. And so WalterLewin concluded that Sirius B has a temperature of 8,000 degrees Kelvin, comparable to our Sun. So now, you have no choice anymore. The only way now that you can explain that Sirius B is 10,000 times weaker, the only way that you can do it is by making the star 100 times smaller. You have no choice anymore. Therefore, you have to accept now the fact that there are stars which have a density of 1,000,000 grams per cubic centimeter. And that is the leftover of stars less than 8 solar mass. When they have burned their hydrogen, when they have burned their helium, they expand, they become big, and they shed off the atmosphere. That nucleus that remains, that nucleus is a white dwarf, and that has a density of about 1,000,000 grams per cubic centimeter. It is 100 times smaller than our Sun. That means the radius of the white dwarf is about the same as the size of the Earth, about 10,000 kilometers, about the radius of the Earth. So you have to think of these stars, these white dwarfs, as being the size of the Earth. They contain about 1 solar mass, maybe a little more, less, and they have a density of 1,000,000 grams per cubic centimeter. So I'd like to show you now a picture of Sirius A and Sirius B. Oh, here you have the famous equation, just to remind you again of how crucial that equation was to come to the conclusion that there are stars that have such a ridiculously high density. Then I have the last one. So now you see here Sirius A, bright one, and you see Sirius B. I don't have to tell you which one is A and which one is B. You see there this very faint star that was discovered by Aldrin Clark, and that we now know is a white dwarf. Can I have the lights, please? So the discovery of white dwarfs was roughly made around 1860. And of course, nowadays we know thousands of white dwarfs. I will now turn to neutron stars. So we know now that stars less than 8 times the mass of the Sun become white dwarfs, and they have used up their nuclear fuel that is available, and now we can go to stars that are more massive. I go to stars that are between 8 solar mass and 25 solar mass. So they're distinctly more massive. New countryman, Thomas Sakar, calculated, from a mechanical calculation, that a white dwarf can never be more massive than 1.4 times the mass of the Sun. For those of you who have had quantum mechanics, you probably have seen that calculation. The reason why a white dwarf is stable is because there is equilibrium between gravity and the degenerate pressure of electrons. The degenerate pressure is a quantum mechanical phenomenon, and if you don't know what that is, that's okay. But once the mass is larger than 1.4 solar masses, Thomas Sakar, for which he got the Nobel Prize, demonstrated that the degenerate pressure of the electrons is not strong enough to hold the gravity, and so the gravity takes over and the white dwarf collapses. He didn't know what would happen, all he said, it will collapse. White dwarf will not be more massive than 1.4 times the mass of the Sun. So now we're talking about stars that originally are between 8 solar mass and 25 solar mass. Hydrogen starts burning, makes helium. Hydrogen ends up, finishes, star shrinks, temperature gets up, helium ignites. Helium is used up, star shrinks, temperature goes up, carbon ignites. Carbon is being used up, core shrinks, temperature goes up, oxygen ignites. And what happens is you get a whole series of nuclear fused chains which finally end with silicon fusing into iron. That's the last cycle. That's when the nuclear fusion stops, because if iron fuses with itself, you don't gain energy, but you have to put in energy. The different cycles, the next cycle always lasts shorter than the previous one. So the hydrogen one lasts shorter than the helium one, lasts shorter than the hydrogen one, and the carbon one lasts shorter than the helium one. And each cycle, each next cycle, has a higher temperature, because remember, you get gravitational collapse, kinetic energy goes up, the heat goes up. So each next cycle lasts shorter, luminosity goes up, temperature goes up. To give you an example, hydrogen typically in these stars burns for about maybe 1 or 2 billion years, and the silicon becomes iron in only 2 days. And when the hydrogen makes helium, the temperature is about 15 million degrees, but when silicon goes to iron, the temperature is about 3 billion degrees. There's an enormous difference between these various cycles. Now, this silicon is going to make an iron core. And the mass of this iron core can be enormous, because the star started with 8 to 25 solar mass. And so it is very likely that the iron core becomes more massive than 1.4 solar mass. And that's not allowed, it cannot be a white dwarf. So the moment that the iron core is being pushed over the Chandra-Shakar limit, it collapses. And we now know that what happens is that a neutron star is formed. A neutron star has a radius of only 10 kilometers. The white dwarf has a radius of 10,000 kilometers. So this inner core, which is 10,000 kilometers at one point, white dwarf-like, will then, when it's pushed over the 1.4 solar mass limit, it will collapse into 10 kilometer radius neutron star. That means the electrons are pushed into the protons, and the interior of that star is largely neutrons, not exclusively, but largely neutrons. Now think about it. A 10,000 kilometer star, the white dwarf, now goes down to 10 kilometers. That means its radius becomes 1,000 times smaller. That means its volume becomes 1 billion times smaller. That means the density goes up by a factor of 1 billion. And so the 10 to the 6 grams per cubic centimeter of the white dwarf now becomes 10 to the 15 grams per cubic centimeter. So now you have in your hand a star which is only 10 kilometers across. It has a mass, maybe 2 solar mass. It has to be larger than 1.4. And it has a density of 10 to the 15 grams per cubic centimeter. It goes way beyond our imagination. But that is then what a neutron star would be like. When the 10,000 kilometer white dwarf collapses into a neutron star, the amount of gravitational potential energy that is released, any freshman physicist in my audience should be able to calculate it, what the gravitational potential energy is between 10,000 kilometers and 10 kilometers. It is so enormous, the energy that is released is so enormous that the star produces in less than 1 second 100 times more energy than our sun produces in its entire lifetime. So in 2 seconds, more energy is released. In less than 1 second, more energy is released than our sun radiates in 10 billion years. So the star becomes enormously bright, and we give those stars a name. We call them supernovae. And so we believe that in supernova explosions, that neutron stars can be formed. How were neutron stars discovered? In 1967, graduate student Jocelyn Bell in Cambridge, England, was working with a new radio telescope that was built by her supervisor, Anthony Lewis. And it was Jocelyn's task to every day check the data of this new radio telescope. The data were shown on a strip chart recorder, and so she would look every day at the signals of the strip chart. And one day, she noticed something very strange. She noticed in the strip chart, all of a sudden, a radio pulse, and 1.3 seconds later, another radio pulse, and 1.3 seconds later, another radio pulse, and 1.3 seconds later, again a pulse. Imagine how puzzled she was when she saw that, because it had never been seen before. So clearly she discussed it with Anthony, and at first they decided, well, it's probably an elevator somewhere nearby in a building which is doing this. Maybe a farmer is milking his cows, and that may give us induction, and we made these crazy pulses. But Jocelyn was very persistent, and Jocelyn was able to demonstrate that it really is an astronomical object, because, as you know, stars move from night to night. They're not exactly at the same position. And so she demonstrated, by following the object where they came from, that was moving in the sky in terms of weeks and months. And so it was clear that it was an astronomical object. Then, they believed that they had made the discovery of all time, because they argued, what on earth can send to us every 1.3 seconds a radio pulse? Only the intelligent beings can do that. And so they believed that they had discovered forms of life outside our solar system. So they called that object Little Green Man. And Jocelyn months later found another Little Green Man. Strangely enough, period was also about 1.3 seconds. And so we had Little Green Man 1, Little Green Man 2, and then they realized when they found the third one that they had to abandon the idea of Little Green Man, and that it was an astronomical, new type of astronomical object. And they published their data in 1967. And they didn't quite know what it was, but they made a proposal. They say, well, maybe you see pulsations of a white dwarf, oscillations like this, or maybe you see pulsations of a neutron star. Well, it was Thomas Gold in the United States when he read the paper, who immediately realized that it can only be one thing, and that it can only be a rotating neutron star. And he concluded that on the basis of the fact that the timing between the pulses was so immensely accurate, it was more accurate than 1 part in 10 million, that he said only rotating objects can do that, pulsating objects cannot do that. And of course, it's now well known and well understood that these objects, which are called pulsars, that they are rotating neutron stars. In 1974, Anthony Lewis was awarded the Nobel Prize for the discovery of pulsars. Jocelyn did not share in the Nobel Prize. This is one of the worst cases, I know, in history, of discrimination against women. It is absolutely a scandal, because she discovered them, and did not share in the rebellion. We will never know why the committee in Stockholm made this incredible blunder. Is it because she was a woman? Or is it because she was a graduate student? Or, maybe even worse, she was a graduate student and a woman? We will never know. But it is a blunder that they made of astronomical proportions. I got to know Moscow Jocelyn, I've discussed it with her several times. She is very modest about it. She doesn't really think that she should have had the Nobel Prize. I think she's the only astronomer in the entire world who believes that. Every astrophysicist and every astronomer realizes that it is scandalous that she did not share, and of course, this mistake has unfortunately not been undone. So I'd like to show you Jocelyn in the days that she made this discovery. Can you turn the lights off? Thank you. So you see her here in front of a stack of cards. Those of you who are old enough may remember that this is the way that we had to write in the 60s and 70s our computer programs, IBM machines with punch cards. It was a torture. Small program would be 60 centimeters of cards that you had punched, and then you would run it through a machine that would read those punches, and then the machine sometimes chewed up a few cards, and then of course the program would run. That has changed, but it is interesting that when this picture was taken, she shows the IBM punch cards that undoubtedly she had used. Here is a conception, an artist's conception of a neutron star, and it tries to make you see how we believe that these pulses, these radio pulses, where they originate. It is believed that at the magnetic north pole and at the magnetic south pole, there is a beam of radio emission going out in both directions, North Pole and South Pole. The physics of that is very complicated and not fully understood. But think of it as being a lighthouse. Instead, it's not light, but it is now radio emission. I lost the light on the website. So the idea being that you now have a lighthouse effect in the radio emission, and let us assume now, which is done on this picture, that the axis of rotation does not coincide with the magnetic dipole axis. So the magnetic dipole axis, you can see, I'm in trouble now, it's so dark here that I cannot see what I want to see. Okay, so here you see the axis of rotation, and here you see the magnetic dipole axis. Let's accept this picture for a moment, and I will be the neutron star for now, and the axis of rotation is my body, and here is the north pole, magnetic pole, and here is the south magnetic pole. And I'm now going to rotate. Why don't you give the lights on now? I'm going to rotate. You don't see radio emission. It's going in that direction, it's going in that direction. That's your tough luck. But now it's going to rotate. And now you there will see radio emission, just briefly. And now you will see it very briefly. And this light beam, this radio beam passes you, you will see a pulse. And you will see a pulse, and you will see a pulse, and then you will see again a pulse. You will now say, well, isn't it a little bit artificial that you have to assume that the magnetic dipole axis doesn't coincide with the axis of rotation? Well, I have a surprise for you. You cannot name any object, any planet, or any star for which the two are co-aligned. They're never co-aligned. They're not co-aligned in the Sun, they're not co-aligned in the Earth. The magnetic dipole axis, I think, is about 15 degrees off the axis of rotation. So it is the rule in astronomy. Very rare that they co-align. So it's not artificial at all. Now, of course, I'm not saying that it has to be 90 degrees this angle, but you would still see the same phenomenon of pulses, even if this angle was only 60 degrees, 40 degrees. The whole idea is then that the axis of rotation and the magnetic dipole axis cannot coincide. And the blue lines that you see there are meant to indicate magnetic field lines. I will not further elaborate. That's enough for the slide. You can turn the lights on, but I think you did that already, didn't you? So the idea then exists that neutron stars are formed in supernova explosions. And Professor Stalin at MIT, when he read the paper of the group in Cambridge, immediately realized that if he takes a radio telescope and if he looks at a location where there was a supernova explosion in the past, that he may discover a pulsar. And he selected a very famous supernova that went off in the year 1054. It was discovered by Chinese astronomers, and they called it the guest star. Chinese astronomers were very active because they gave advice to the emperor what the emperor should do and what he should not do. Whether it was time to fight or not to fight, whether perhaps there would be diseases or whether there would be shortage of food. The astronomers were able to interpret the sky and advise the emperor, and therefore the astronomers were very active. And they discovered in 1054 an enormously bright star in the sky, and it was so bright that it could be seen during the day. For weeks on end, it was visible during the day. Imagine you walk on the street and that you see during the day a star in the sky other than the sun. An amazing thing. It was the brightest star in the sky for months and years. Now comes the big surprise. There is no record, anyone else in the world who has seen this star, which was visible during the day for weeks. Yet people must have noticed it. And there must have been scientists who would think to write it down. Now, I happen to be Dutch, and you can't blame the Dutch for not having noticed this star because it always rains in the Netherlands, so it's always clouds. So we are off the hook. So think of Italy, think of Greece, think of Spain. None wrote down that there was a star in the sky that was visible during the day. It will always remain a mystery, but nevertheless, that supernova in 1054 exploded at a distance of about 6,000 light years, and when it explodes, the star, except the nucleus of the neutron star, which remains behind, whatever matter is in the star is thrown off with an enormous speed of about 20,000 kilometers per second, and therefore if you look several hundred or several thousand years later in the sky, you see a nebula around the star, which is then the result of this matter of the star flowing out. And that was also the case of 1054. That nebula is very famous. It has a name. We call it the Crab Nebula. I will show you a picture of the Crab Nebula. And so what Dave Stalin did, he pointed one of the MIT radio telescopes at the Crab Nebula, and he hoped to discover a pulsar, and actually did. He did discover a pulsar, and the period of that pulsar turned out to be 33 milliseconds. So this neutron star rotates around 30 times per second, whereas Jocelyn's only 1.3 seconds for one rotation. This rotates around 33 milliseconds. Now, if you try to think about this for a minute, an object size of about 10 kilometers, a density of 10 to the 15 grams per cubic centimeter, and rotating approximately 30 times per second. Totally mind-boggling. It is beyond words. And if it doesn't turn you on, you shouldn't be here in the first place. Okay, I will show you the graph map. And you turn the lights off. You see the graph map? And for those of you who are sitting very close to the screen, you can see two stars in the middle. If you're far away, you will not see that. But there are really two stars here. You have to sit very close. It is the southern one of the two that is the neutron star. So the people who are sitting very close here to this one, you can see in the middle here two stars. And the most southern one is the neutron star. So this object, this nebulae, is at a distance of 6,000 light years from us. So what you see now was the situation 6,000 years ago. From here to here is about 11 light years, to give you an idea. And this is the material of the star that is still thrown out with a speed of about 20,000 kilometers per second. In terms of the size in the sky, if you compare this with the size of the moon would be about 6 times larger. So the moon would be this big, and the Crab Nebula this size, but of course that distance of 6,000 light years, and so this distance here, therefore enormous, 11 light years. So you have seen now a neutron star. Now we move to a galaxy which is 25 million light years away from us. So the light that you see from this galaxy was emitted 25 million years ago. And in 1999, Supernova was discovered in this galaxy, this one. And you can see for yourself, this is one star, that one star is almost as bright as the sum of all the other stars. What you see here is a total of about 100 billion stars. You cannot separate them because the resolution of the telescope cannot see them as individual stars. If you add up all this light, you get very close to this light. Our own galaxy has also about 100 billion, 200 billion stars. And so, during the early weeks and months of a supernova, it outshines effectively all the stars in the galaxy, or at least its luminosity is comparable to all the stars in the galaxy. Then I have light speed. So if I briefly summarize before I get into the black holes, stars with a mass between lower than 8 solar mass, have a lifetime, will be relatively long because they are low mass. Ultimately, they will go through a red giant phase, they will lose the atmosphere, and what is left over is a white dwarf. That's the fate that our sun will go through in about 5 billion years. Then I discussed stars between 8 solar mass and 25. They will undergo supernova explosion, and they will form a neutron star. And the reason why it becomes a neutron star is that when the iron core becomes more massive than 1.4 solar masses, unless the car says, sorry, that's not allowed, it implodes, and it becomes 1,000 times smaller. So now, we have to go to black holes. So now what I do, I go to stars which have a mass larger than 25 solar masses. And stars larger than 25 solar masses do everything exactly the same as stars of about 25 solar masses. They burn the hydrogen, the helium, the carbon, the oxygen, the neon, the silicon, and they stop at iron. They can't go beyond iron because I told you that iron fuses with itself. It costs energy. It doesn't create energy. So they go all the way up to iron. But, now there is a big but. Thomas Leclerc demonstrated that a white dwarf cannot be more massive than 1.4 times the mass of the Sun. It can be shown that a neutron star cannot be more massive than about 3 times the mass of the Sun. And if a neutron star becomes more than 3 times the mass of the Sun, there is no quantum mechanics anymore that can stop the implosion. Gravity takes over. Quantum mechanics is powerless, and gravity turns the entire star into a point of 0 dimension, 0 size. We call that a singularity. So all the mass, say 4 or 5 solar masses, is in a point which has no dimension, so the density is infinitely high, and the temperature is infinitely high. And that's what we call a black hole. Physics can do no work on the singularity because there is not yet a theory of quantum gravity. So it stops as far as the singularity is concerned. However, I can tell you a few things which give you still a little insight into the idea of a black hole. Schwarzschild demonstrated that a solution of Einstein's field equation leads to a point with size 0, which is the singularity. And let's assume that here is that singularity. Then you can define around the singularity a sphere, which is not a circle, but it is a sphere, which has a certain radius r, and the singularity has a mass capital M, which probably is more than 3 solar mass, 4, 5, 6, maybe 10. We call this sphere the event horizon. And what that means is that if you're inside the event horizon, you can never escape, you can never go through the event horizon, because you need a speed larger than the speed of light. So nothing can get out from inside the event horizon. Light itself cannot go out. X-rays cannot go out. Any electromagnetic radiation, nothing can go out. But as long as you are outside the event horizon, then you may need a very high speed, but it is a speed lower than the speed of light. So you can then escape the event horizon. I will show you a relation which is easy to derive between the radius of the event horizon and the mass of the singularity. And that equation is that the radius of the event horizon is 2 times the mass of the singularity, we call that mass black hole, times the gravitational constant, that you know from Newton's theory of gravity, divided by c squared. C is the speed of sound. When you see this equation, you have all the right to say, well, so what? What is this equation telling us? I will tell you what this equation is telling us. And you may never forget it when I tell you. If you put in this m the mass of our sun, then r becomes 3 kilometers. But since r is linearly proportional with m, it means that if you have a singularity, a black hole of 10,000 times the mass of the sun, then the event horizon is 30,000 kilometers. It's always 3 times higher in kilometers than the mass is in solar mass. So I repeat, a 1 solar mass black hole, if they existed, would have a radius of 3 kilometers. 10 solar mass black hole would be 30 kilometers. 1,000 solar mass black hole would be 3,000 kilometers. A 4 million solar mass black hole, and we think there is one in the center of our galaxy, a 4 million solar mass black hole would have an event radius of 12 million kilometers. So it's strictly linear with, and is strictly linear with r. How were black holes discovered? In 1971, a new type of astronomical object was discovered, and we gave that the name X-ray binaries. I have worked practically my whole career at MIT on X-ray binaries. An X-ray binary is a system that I will show you, but before I do that, I want to do this equation once more. So you know now what it means. It tells you, if you know the mass of the singularity, you can then calculate the radius of the event horizon, which in this case is a sphere. You can turn the lights off now, thank you. This is a binary system. 2 stars. This star could be a star like our sun, but it could also be 10 times more massive than our sun. But the star is alive. It is clearly getting its energy from nuclear fusion. Here is a very small object, it's very massive. It could be a white dwarf, it could be a neutron star, and as I will convince you, it could be a black hole. And if these two are very close to each other, then it is possible that at this point in this star, the gravitational force towards the center of the star is smaller than the gravitational force in this direction. And when that happens, it's energetically more favorable for this matter to leave the star and to go to the compact object. We call that mass transfer. We call this star the donor star, and we call this star the accretor. Around the accretor is always a disk, which is not very important in what follows, but at least I want to mention it because you see it clearly. It's obvious that there has to be a disk, because if you have the light, please. This is, after all, light on, please. This is a binary system. So here is the donor star, and here is the small star, and they go around each other. So if matter goes from this star to this star, it could never go along a straight line, because it has a velocity in this direction. And so the net velocity is the vectorial sum between this velocity, and so that means it goes around in a circle, and it spirals in, and then finally it ends up on the surface of the star, the compact object, if it has a surface. I want it to have a surface now, and therefore I will assume just for a minute that it is a neutron star. But I'm on my way to convincing you that it could be a black hole. I need this step in between. Let's assume that it is a neutron star. If you throw matter onto a neutron star, independent of what the mass of that matter is, it reaches the surface of the neutron star with half the speed of light. That's the result of the fact that the gravitational pull very close to the neutron star is enormous, because it's 10 kilometers and its mass is about 2 solar mass. So you get an enormous acceleration and it slams onto the neutron star with half the speed of light, and that's independent of the mass. Do you people in India eat marshmallows? Who eats marshmallows? Not too many people. Who knows what a marshmallow is? Okay, that's good enough. If you have a marshmallow in your hand, you don't even know yet. It may weigh 1 or 2 grams. All sugar, very bad for you, but that's a bit. So you don't even know that you have it in your hand. It's so enormously light. If you throw that on a neutron star, and it hits the neutron star, the energy that is released is comparable to the atomic bomb that was thrown on Hiroshima. That tells you what it means when something hits the star with half the speed of light. Tremendous amount of kinetic energy is released. The temperature becomes so high, typically 100 million degrees Kelvin, and at 100 million degrees Kelvin, the object will almost exclusively radiate in X-rays. I assume that most of you know that if your temperature is low, like our bodies, we radiate infrared radiation. If you look at the stove where the coals are 2000 degrees, they produce red light, and the hotter you make them, the shorter the wavelength is, and if you are in 100 million degrees, then almost exclusively X-rays, which have a very, very small wavelength. So, this object is the X-ray emitter, and this is an optical object that you can see with an optical telescope on the ground. And the X-rays, these X-ray binaries, that in this combination we discovered in 1971. Before that, we had no idea actually why there are such strong X-ray sources in the sky. But now we know that they are X-ray binaries, and we understand now why they do emit so much energy. So now I'm going to polish my way to black holes. If you're very smart, you will say, yeah, you could never see X-rays from a black hole because a black hole has no surface. And as soon as the matter that spirals in, as soon as it gets inside the event horizon here on the black hole, no X-rays can ever come out. That's a reasonable argument, but the reason why we do see X-rays from black holes, that when the matter approaches the event horizon, it also is already enormously hot, and therefore it radiates X-rays. But we only see the X-rays that come from outside the event horizon, not from the ones inside the event. But we do see X-rays. Now I'm going to take a strange road that will puzzle you a little, but at the end you will see why I go that road. All of you in high school have learned about Doppler of sound. You probably have had a demonstration that if the sound source of a certain frequency moves towards you, you will hear a higher pitch than the sound source itself, And if it moves away from you, you will hear a lower pitch. I will demonstrate that to you, although most of you have probably heard this already. I have here a 4,000 Hertz tuning fork, and I have practiced a little bit. I think I can move my hand towards you. It's about 1 meter per second. Cannot go much faster. So I can go 1 meter per second and back 1 meter per second. When I go towards you 1 meter per second, the pitch will go up by 0.3% because 1 meter per second is 0.3% of the speed of sound. So the pitch will go up by 12 Hertz. So when I do this, you don't hear 4,000, but you hear 4,012. Well, clearly when you sit there, you're not going to tell me if you hear 4,012. But now what I do, I move it back. And now you hear 12 Hertz below 4,000. And if I do that back and forth a few times, you will distinctly hear high frequency, low frequency, high frequency, low frequency. Because you hear the difference now between this direction and this direction. I will first do it in your direction, and then I will repeat in your direction. Those who are sitting on the balcony, pretty far away, I'm not sure whether my tuning fork is strong enough that you can hear it. I'll make it up. I'll do it again. Did anyone of you hear this phenomenon or not yet? Raise your hand if you heard Doppler. Okay, I'll do it once more. I'll do it also in your direction because if I use that direction, they have a stronger effect than you do. Here? Okay. Now, suppose you have not listened. But suppose you have recorded on a strip chart recorder frequency as a function of time. So you were sleeping. And so when you wake up, you look at your strip chart recorder. And what do you see? Let's assume that this is 4,000 Hertz. And that this is frequency, call that F, and that this is time. I call that T. So when I move my hand to you, if I move my hand pretty constant, you will hear 4,012. When I move my hand away from you, you will hear 12 Hertz lower. And I do this very fast. And then I come towards you, and you hear 12 Hertz higher. And then you hear 12 Hertz lower. And so on. So you see this strip chart. What can you tell from this strip chart? Just by looking at this graph. There are two things that you can tell. For one, you can tell how long it took me to move my arm out and in. That's obvious, because this is the time from here to here. That must be the time that it took me to move my hand back and forth. Agree? So this curve has intrinsically in it, if I call that the period of my complete oscillation. You can tell that immediately by looking at how many seconds that was. But there is more that you can tell. You can even tell the speed with which I moved my hand. Because if I tell you, and the strict start recorder will tell you that this is 12 Hz higher, assume that this is also 12 Hz higher, then the fact that this is 12 Hz higher will tell you that I moved my hand with 1 meter per second. Because if I had moved my hand with 2 meters per second, this wouldn't be 12 Hz, but this would be 24 Hz. In other words, it is this amplitude that tells you the speed of my hand. So you learn two things. You learn the periods back and forth, and you can tell with what speed I move my hand. Hold on to this, because I want to end up with black holes, and I need them. All stars in the sky, when you look at them, and you look at them with a spectrometer, you see a beautiful spectrum, all the colors, red all the way to blue, but all stars have in their spectrum black lines. We call them absorption lines. In our sun there are thousands of them. We call them Fraunhofer absorption lines in the sun. All stars have these absorption lines. So that particular frequency or that particular wavelength is missing or is highly suppressed. Let's suppose for now that the donor star emits sound. So the donor star is going around like this. And you listen to the sound of the donor star. You will not see this. But what will you hear? What will you see or hear? So I will rotate the sound source very shortly in a circle around. What will you now hear in terms of Doppler? You will see a sinusoid, and you will not see it like this, but you will see a nice sinusoid, which I will draw on the board. Let's assume that it is 4,000, but that's not important, which assume. So you will see something like this. You were not paying attention, you fell asleep during my lecture, but you recorded it. And so you look at your strip chart recorders, and this is what you will see. What now will you learn? You will learn that the time for this sound source, the donor star, to go around, which is the period of the donor star, the period in that binary system, you will immediately be able to tell that it is from here to here. That is the period of the binary system. But you will also know the speed of the donor star, because the speed follows from this. If the speed is high, the sinusoid will be high. If the speed is low, the sinusoid will be low. So you learn from this curve two things. The orbital period, the donor star, and the speed of the donor star in orbit. Unfortunately, donor stars do not emit sound. But if you look at their spectra, they have absorption lines in their spectra, dark lines in the spectra. And electromagnetic radiation also has Doppler shift. If electromagnetic radiation comes to you, for instance, light, then the colors are all shifted in the direction of blue. We call that blue shift. And if the light source goes away from you, all the colors are shifted towards the red, and we call that red shift. And so if you follow the absorption line of a star, as the star goes around, there are times that the star comes to you, then you would see the absorption line moving through the blue, and when the star goes away from you, you would see the absorption line going towards the red. And that was discovered in 1971 from a very famous X-ray source, and I will show you in principle the idea. You can make it darker. So there you see on the screen, not real data, but you see the spectrum of the star. Astronomers could probably tell the temperature of the star by looking at these colors, but that's not important now. Here you see an absorption line, and notice that this absorption line is slowly, well, you don't see that it is slow, you can take my word for it, it slowly goes towards the red, and then it stops here. That's the largest excursion that it makes. That means during this time, from here to here, the star was moving away from you. And the time from here to here, it's going in the direction of the blue, the star was coming to you. So what can you tell now if you have this data in your hand from a donor star, and this data is taken with an optical telescope on the ground? You can immediately tell the orbital period, because the orbital period is, of course, twice the time between this point and this point. Because it has to go here and back. So you know the orbital period. But you also know the speed of the donor star, because if the speed is very high, this point wouldn't be farther to the left than it is now. If the speed were low, it wouldn't go as far to the left. So it's completely analogous as sound. So you learn exactly the same things that you learn from sound. You learn the orbital period, and you learn the speed of the donor in orbit, just as we learned with the rotating sun source. We learn the period, and we learn the speed. So if I can have the lights now, then we will assume that this is a donor star, and we just make the ridiculous assumption that the donor star emits . Can you hear the sound of the score? I'll try it, but it's probably too fast. Yeah, this is too fast. So I have to change the battery, and that will take too much time. If I rotated it around about my head, like this, you would hear the sinusoidal variation. You would hear the pitch high, pitch low, pitch high, and pitch low. So, optical astronomers measured that phenomenon from a donor star of the very famous X-ray sort, which we call Cygnus X1. So they knew the orbital period was 5.6 days, they knew the speed of the donor star, they knew Kepler's law, and when they combined all this data, they were able to calculate, which is not so difficult, I do it in my lectures, you can calculate what the lower limit is of the compact object. You cannot calculate the mass, but you can tell the lower limit. You say it has to be more massive than a certain value. And they found that the mass of this compact object in the X-ray binary was more than 3 times the mass of the Sun, and they both concluded that the X-ray binary wasn't a black hole. And it's now no question anymore. We now know very precisely the mass of that black hole. One of my own graduate students, previous graduate student, was very instrumental last year in calculating, observing that the mass of the donor star, the mass of the equator is 15 times the mass of the sun. So the black hole, 15 solar masses, and the donor star is 30 solar masses. And so this was then the discovery of black holes, stellar mass black holes. Can you turn the lights off? When we come home tonight, you can tell your friends, parents, that you now know what a white dwarf is, you know how they were discovered, and you can also tell them that I showed you a white dwarf, Sirius B. You can tell them that you know what a neutron star is, you know how neutron stars are formed, and you can tell them that I showed you a neutron star, even though it wasn't so easy to see for many of you, was the star in the pandemic. So I think what I owe you, I'm not showing you a black hole, but at least you can hold. You can see, you can say, I now know how black holes work. And you even show us a second. That would be very impressive, wouldn't it? So I decided to show you a black hole. This is a black hole. Not very satisfying, right? So what I will also show you is the optical image of the donor star. It's a very bright star, 30 solar mass star, easy to detect even with a small telescope. I will show you that star, among other stars. It's a negative, the star is black, sky is white. We do that often in astronomy. At least then, at home you can also say that, well, we saw a donor star, and we know that there is a black hole in orbit with that star. And the donor star of Sirius S1 is this star. Orbital period 5.6 days, and the black hole is mass about 15 solar masses. So, as far as stars is concerned, there is life after death, provided that they find the right companion. And it is my wish that all of you, during life, not after death, find the right companion, radiate, and be happy. Thank you.
Thank you, Professor WalterLewin, for the brilliant lecture. Please join me in a round of applause for him.
Okay.